Hello there, good morning or good afternoon, wherever you are, and welcome to today's Telecoms.com intelligence webinar, produced in association with F5 Networks. My name is Tim Skinner, and I am the content manager for the Telecoms.com intelligence series. Today's webinar will be looking at the evolution of traffic steering in the Gi-LAN. We will focus on how emerging technologies and external market forces are compelling operators into a fundamental rethink of how traffic is routed in the mobile network. Mobile network operators are being faced with the evolving challenge of managing unprecedented volumes of data growth, while simultaneously optimizing network resources and lowering costs. Meanwhile, new business models are emerging which can help drive additional revenue streams, increase profitability, and improve quality of service for subscribers. To help manage the data explosion and the transmission of increased volumes of data in varying sizes and forms, with varying destinations and for varying demographics, we will look at how the development of software-defined networking, or SDN, can assist in terms of context-aware traffic steering. We will also be touching on how network functions virtualization, or NFV, is able to assist in terms of automated and virtualized service chaining. So, on the agenda for today, we've got a fantastic presentation coming up from F5. Regular viewers of our webinars may be familiar with Bart Salatz, who is the Senior Manager of Field Systems Engineering for F5 Networks. Bart has developed an extensive history in the telecoms industry, having previously taken up IP consulting and technical leadership positions at Juniper Networks, Redback Networks, and Alcatel-Lucent. In all, he has been involved with both fixed and mobile broadband IP network design for more than 15 years. So with Bart at the helm today, you're in great hands for what will be a great presentation, I'm sure. At the end of the webinar, we will have some time for Q&A with Bart. You can submit a question for him at any time during the presentation. Simply type your comment into the dialog box that you can see on this page. Responses will appear at the end of the presentation. But to set the scene, I'm going to give a very quick introduction before I hand over to Bart, so that we can summarise where the industry is today and also understand where factors are influencing the move towards intelligent traffic management practices. In December last year, a white paper produced by Telecoms.com Intelligence revealed some insight into the growth of IP and internet-based traffic. By 2020, more than 20 billion devices will be connected to the internet, and global IP traffic will triple at a compound annual growth rate of 21%. Adding to this, in January, the GSA released some figures which underlines the growth of LTE network infrastructure across the world in 2014. According to the association, 360 global operators have already commercially launched LTE networks and services in 124 countries. 611 operators are investing in LTE across 174 countries, and this comprises of 566 operator network deployment commitments in 166 countries, of which 360 networks have launched, and 45 pre-commitment trials are in a further 8 countries. Compounding the figures released from the GSA, we ran a few questions about LTE deployments in our most recent annual industry survey. Of the 2,000 industry professionals that we polled, 65% identified LTE network rollout and/or expansion as a priority for 2015. Just under 40% of our respondents also believe that more than 50% of existing 3G customers will be covered and served by LTE services by the end of the year. So while there's been some impressive growth of LTE network deployment in the past 12 months, there appears to be some way to go in the next year. As a result of LTE booming worldwide, we are left with a distinct shift towards more transmission of IP-based data, and consumer expectations mean that operators have quite simply got to deal with it. How they deal with it exactly is something that Bart will go into in greater detail. On the face of things though, operators are left with little option but to evaluate alternative methods for managing network infrastructure to ensure high quality delivery of LTE-based services. According to our survey, 86% of respondents identified consumer demand for data-driven services as one of the primary motivators for deploying or expanding LTE networks. We are now living in an age where every service we enjoy as consumers has a high level of personalization about it. Data is personalized, content is personalized, and such high volumes of personalized information are forcing a need to optimize packet steering and ensure that correct services are being deployed in an automated and yes personalized fashion. As we have seen since the start of the year, particularly with BT's acquisition of EE, operators are increasingly viewing a multi-play converged portfolio of service offerings as an important shift in focus. The Telecoms.com Intelligence Annual Industry Survey 2015 asked our respondents some questions about multiplay strategies, and 66% believe that multiplay operators will have achieved significant advantage over pure play operators within 5 years, as you can see at the bottom of the table here. That statistic serves to illustrate the pressure that operators are feeling at the moment to differentiate their service offerings across a range of technology platforms, and that in itself presents a new headache as to how to manage traffic and service delivery more intelligently. In the past couple of years, SDN and NFV have become industry buzzwords commonly associated with the next generation of network and traffic management. While SDN refers more specifically to the routing and steering of traffic in a more intelligent way, NFV is commonly associated with more agile service delivery based on virtualized hardware platforms. The two philosophies combined can present operators with intelligent and personalized traffic steering capabilities based on the content being directed, the context of the transmission, and is flexible to current network conditions and requirements. And so, to that extent, multiple operators have been engaging with proof of concept trials investigating automated service chaining capabilities of network functions in an NFV environment. Last year saw Telenor investigate subscriber-aware Gi-LAN virtualization in an ETSI NFV proof of concept trial, which attempted to verify methods for automating service chaining and demonstrates how virtualization can enable more advanced programmability of network-driven functions selected by subscribers on a self-service portal, as well as the rapid introduction of new functions to increase service deployment velocity. Telefonica were also engaging in similar trials at the time, illustrating the importance of this to operators today. And it is about these principles that Bart will speak in greater depth today. And so, without any further ado, I'm going to hand over right now for Bart's presentation. Once again, we will be allowing time for any questions after Bart's presentation, so please do use the comments box on the side of the screen to submit your query. Bart, it's over to you.
Okay, thank you very much, Tim, for that introduction. Welcome, everyone, and good afternoon. So as Tim already pictured, I'm going to talk a bit about intelligent traffic steering and service chaining, which has become a fairly hot topic in the industry, and specifically on the mobile Gi-LAN, and that's also the area where we are particularly going to zoom in on. So what I'm going to talk about a little bit is first look at how traditionally Gi-LANs have been built up, because there's many different components that you have on the Gi-LAN, and how that type of architecture, which has been very successful until now, is presenting some challenges looking at all the new evolutions and the traffic growth that is coming towards the operators. So instead of going from what people have been doing traditionally, very static traffic steering, very little flexibility, people are looking into a much more dynamic fashion and have it completely policy controlled, completely policy driven on how you engineer all the traffic flows on the Gi-LAN. So I'll walk you through how it was done before and how people are now trying to do it going forward. It's eventually even moving into a full-blown NFV type of architecture. So Why is this such a hot topic? Well, the reason why it's such a hot topic is because the Gi-LAN has become very complex over the last couple of years. And I realize not all mobile operator networks are exactly the same. We see a lot of variations. Some of them have relatively simple Gi-LAN networks, but I've seen some of them which are very, very complex. And that is because these networks have grown historically, where people have been adding different types of optimization platforms on the Gi-LAN, different types of value-added service platforms like parental control, security appliances, etc. And then over time, people ran out of IPv4 addresses, so they had to add carrier-grade NAT, they had to add GI firewalls. Some of them have been adding VPI platforms. So you have this ecosystem of lots of different boxes that are interconnected with one another in a fairly static fashion and very complex to manage. Looking at the evolution now in the internet, where there is explosive data growth, and especially those operators who started deploying LTE have experienced that. As soon as you deploy LTE, there is a massive growth of traffic in the network. And obviously that means that in this whole static environment, all of those components that you have on the Gi-LAN need to scale accordingly. And that is economically not really a viable business model going forward. So that is one challenge. The other challenge is the increasing nature of security attacks that we see on the internet. LTE is an all-IP architecture, so essentially you're exposing yourself for all your service offerings to whatever type of security attacks happen in the industry, and they become more and more sophisticated as well. So you not only need to scale the architecture, at the same time you need to protect that architecture from malicious users who are trying to attack both your infrastructure as well as your end users. And last but not least, mobile service providers always look for new ways to monetize their network, and they need to be able to introduce new services. And in this complex ecosystem of all these devices statically interconnected with one another, it has become very, very complex to introduce new services. So if anyone comes up with an idea of a new service, just getting it engineered and validated and completely foolproofed is taking a lot of time and investment, and that's not really the right way forward. People are really looking at something that makes it much easier to introduce new services and still keep up with the scale and the security attacks that you're being exposed to. So ultimately, complex networks, I always tend to say complexity is the biggest enemy of stability. So the more complex your network is, the more it is prone to configuration errors, the more it is prone to stability issues, the higher the cost is going to be to maintain and operate a network, because you have a multitude of vendors, multitude of platforms, multitude of operating systems in there. And as I said before, it takes a lot of time to introduce new services, which makes the cost of new service introduction very high as well. And all of that ultimately leads to lower customer satisfaction, right? And this is essentially what you should be doing looking at the Gi-LAN. Make it simpler on the one hand, make it more dynamic and flexible on the other hand, but don't sacrifice on the scalability of the solution, and don't sacrifice on your ability to secure that infrastructure. So what are the main things that are causing concern for service providers these days? And it's not only concerns, it's things that you have to take into account when you sort of build your next generation Gi-LAN architecture. One area of concern is obviously the massive increase in SSL traffic. So as a result of all the NSA revelations, the Snowden revelations, we've seen a massive increase in the amount of SSL traffic on the network. And what we see in Europe, at least, is that on most mobile networks these days, between 40 and 50% of the traffic is encrypted. So that means that between 40 and 50% of the traffic, you can't really do any content optimization anymore. You can't do any content filtering anymore. So that, to a certain degree, limits your ability to take very granular actions on traffic flows. And the major impact here is a shift of people looking into content optimization techniques versus looking at TCP optimization techniques. The other area is the evolution in the radio architectures, right? I mean, everybody's rolling out, or almost everybody's rolling out LTE these days. The next step is LTE Advanced, which is going to be another step upward in terms of scalability requirements for your network. So you need to be able to scale that Gi-LAN in the same way that your radio infrastructure is scaling. And as I will explain in a minute, the way these networks or the Gi-LAN architectures are being built today is not really suitable for getting you through that LTE and LTE Advanced type of massive traffic increase. DDoS mitigation, obviously, mobile networks are obviously very vulnerable also to security attacks. And tomorrow, if you do voice over LTE, all your voice communication is going to be IP-based as well, and therefore it's going to be vulnerable to traditional IP-based attacks, just like the internet is today. So you have to make sure you completely secure this type of architecture. Last but not least, everybody's talking about an evolution from a physical environment to a full-blown virtual environment. So network function virtualization is an area where there is a lot of investment currently, lots of POCs going on, some mobile operators being fairly aggressive in terms of rolling out virtual packet cores, virtual Gi-LAN architectures. So whatever type of new Gi-LAN architecture you invest in today, you have to be sure that that can evolve seamlessly to an NFV environment. Make sure that that's not going to require a forklift upgrade where you need to rip out all components and completely architect with different types of vendors, different type of operating systems. So make sure that whatever vendor, whatever technology you invest in, you can move in a step-by-step fashion to a full physical environment, which is what is the case today, into a full NFV environment within the next 3 to 5 years. So let's have a quick look at how traditionally Gi-LANs have been built and how people have been doing traffic steering and service chaining in these types of environments. So typically the way this architecture looks was like you have your GGSN P gateway, which terminates all your mobile subscribers, and then if the mobile operator offered some video optimization capabilities, or if it offered some parental control type of services, etc. What they typically did is they had a router in there which just forwards all HTTP traffic or all port 80 traffic into a data center where you have all these value-added services and where you have all these optimization platforms. So essentially that was a rather simple approach to do. And it has been proven to work very well, but there's a couple of challenges with this architecture when you move forward, when you go into LTE type of environments. And the reason is that if you continue to send all port 80 traffic to all these value-added service platforms, there's a lot of that traffic for which the optimization platform or for which the value-added service platform is not really adding value. So if you need to scale up all these systems for the traffic, you're scaling them up unnecessarily high. So what people have been asking for is a more intelligent way of steering traffic to a video optimization platform, or a more intelligent way to steer traffic to a parental control system. More policy controlled and much more granular. And I'll give a few examples of typical use cases that we see now in the industry where people are looking at how can I, starting from this architecture, how can I evolve that to a model where I start to make much more efficient use of all these individual VAS and optimization platforms without just sending all port 80 traffic from all subscribers in a chain through all these VAS and optimization platforms. So the way you do that is essentially by putting a more intelligent device in line here. And that intelligent device, and we call it the steering platform here, essentially is doing two things. One is PCB optimization. So as I said in the introduction, a lot of the attention is now shifting from doing traditional video optimization into TCP optimization. And the reason is simple. There is more and more SSL traffic, which means that less and less video and less content in general can be optimized. Because today, if half of your traffic is already encrypted, then it means that half of the traffic can no longer be content optimized. However, whether things are encrypted or not, whether it's HTTP or HTTPS, at the end of the day, all that traffic rides on top of a TCP session. So TCP optimization will continue to work, and will continue to work for more than 90% of all the traffic in the mobile network, because that's what we see typically. Between 90 and 95% of all traffic is TCP. So from that perspective, if some function on the Gi-LAN needs to be executed on 90 to 95% of the traffic, it makes more sense to do that inline rather than to do it in a data center where you steer the traffic to. Because it doesn't make sense to do an intelligent steering function to something that needs to process 95% of the traffic. That is always going to be more efficient to put that inline and have that as an inline enforcement function. So TCP optimization is one thing that you can do on such an intelligent steering platform. The second thing it does is it moves you from that traditional port 80 static steering model into a much more intelligent and dynamic steering model. And sometimes we call that context-aware and policy-driven traffic steering. Context-aware in the sense that for every packet that goes into the Gi-LAN, we know exactly which user it is, what radio access network it comes from, and then we can take an intelligent decision, much more intelligent than just looking at the fact that this is an HTTP packet. And we take that context into account to determine which of these vast services and which of these optimization platforms need to process the traffic. So for every single packet that goes into the steering platform, you're going to take an intelligent decision on what exactly we're going to do with it from a steering and service chaining perspective. So just one word on TCP optimization. Obviously, the focus of this presentation is more on the steering and service chaining aspect, because it is so important and it's such a hot topic as well in the industry. I just want to spend a few words on that. So, as I said, 90 to 95% of your traffic is TCP, and of that traffic set, the majority is sort of halfway split between HTTP and HTTPS. And TCP optimization essentially allows you to do two things. Number one is it allows you to get higher throughput on the network. So if you do a large file transfer or you do a video streaming, with TCP optimization you will get higher bandwidth. So you make more efficient use of the spectrum, the radio spectrum, by doing smart things at the TCP layer. And as you can see on the slide here, that applies both to 3G networks as well as to 4G networks. You also see that we make a distinction here between when you have good coverage and when you have poor coverage. If there is poor coverage, then usually the optimizer gives even more benefits. Why is that? Because in poor coverage, you randomly lose packets, and a TCP optimizer is smarter in the way it deals with packet loss on a mobile network than a traditional TCP stack on a Linux server somewhere on the internet is. So that's why you see the differences between good coverage versus poor coverage. And then next to optimizing the bandwidth and squeezing more bandwidth out of your radio assets, the other thing the optimizer does is it allows you to load your web pages faster. So on the picture here, the dark blue bar represents a large file download. So this is typically a speed test, getting the maximum throughput out of the radio network. The light blue bar represents how much faster can you load a web page. Because a web page is very different from a large file download. A web page is typically composed out of a series of small objects. So you have a lot of transactions going back and forth. And a mobile network typically has much more latency than a fixed network. So it's the latency that typically impacts web page load times. And as you can see, both of these things, and both of them are important for a subscriber's quality of experience, both of them can actually be significantly improved by doing TCP optimization inline. Now going back to intelligent traffic steering, so context-aware and policy-driven. So what does that mean? So when a packet comes into the intelligent steering device, or the TCP flow, if you will, then the intelligent steering device has the knowledge about which subscriber is behind the packet. He has knowledge about what is the radio access technology type. So he knows whether it comes from 2G, 3G, LTE, and if you have a Wi-Fi integration, it can actually be Wi-Fi as well. So you can have information about that. It has information about the device type. Is this an Android, an iOS? Is this a tablet, a smartphone, or is it a dongle on a laptop? It has knowledge about the application. So you can have a deep packet inspection engine which looks deep into the packet and figures out what application does this packet represent. Location information, where is it actually coming from? Where is that user located? And then even congestion levels. We can even get information around what is the congestion level of the area where that user at that point in time is. And then all this type of context, which we learn either from a PCRF, we can learn it from radius records from which the P gateway sends us, we can learn it from the data plane itself by having a deep packet inspection, looking deeper into the packet. By taking all these factors into account, we can now craft policies where we specify, like, if criteria A equals A, then we take this action. If it's something else, we take another action. And I'll walk you through a couple of examples on how we can do that. So let's take here a simple example, right? So you have a PCRF, and the PCRF has information about subscribers. In this case, he has information about John and Paul, and the PCRF tells the steering device here whether a user has signed up for a parental control service or not. In the past, mobile operators have typically been segregating such services into different APNs on the mobile infrastructure, and then every APN represents a different service. But of course, if you start offering different service packages, it becomes fairly complex and fairly unmanageable, really, to have many APNs in the mobile infrastructure. So with this type of architecture, you can actually have all subscribers still in the same APN, but having the steering device now take the decision on what type of service functions need to be invoked for any particular subscribers. So that is subscriber-based control. The PCRF will tell us what type of service that subscriber has opted in for. The other type of policy that we've configured here in this example is video optimization. So today, many mobile operators have invested in video optimization. It provides benefits on 3G networks, but some of them have some doubts on whether they should enable this technology on LTE or not. But the challenge here is obviously that all your traffic comes out of that same P gateway. 2G, 3G, LTE traffic comes out of the same device, and users are in the same APN. So now the steering device, he has that knowledge about whether the subscriber is on 2G, 3G, or LTE, and he can take an intelligent decision. If he sees HTTP traffic coming in from the 3G network, he's going to steer it to the video optimizer. On the other hand, if it comes in from the from the 4G network, he will bypass the video optimizer. So let's go through a couple of the use cases here. So if John is on a 3G network and he's sending an HTTP request towards the internet, the steering device intercepts that request. He looks into, this is user John, so he didn't opt in for parental control, but he is on a 3G network now, so I'm going to steer his HTTP traffic through the video optimizer, just like it was done before in the 3G network where all video was optimized. So in that case, the steering goes to the video optimizer, and then traffic flows straight through to the internet. If John now moves to LTE coverage, the P gateway will send us a radius update so that the steering device knows, okay, this user with this IP address now moved to LTE coverage, and now the steering action is modified. He will no longer be steered to the video optimizer. He will get a straight line straight to the internet. What this actually does is it allows you to more efficiently use your VAS and optimization services. You are in full control now of what traffic is going to each of these VAS and optimization platforms. And if you have an investment in video optimization and you want to continue use that for 3G, but you don't want to cope with the LTE traffic growth, you don't want to continue scale this infrastructure for the LTE traffic growth, then this is a mechanism to do that. So we continue to use that existing deployed infrastructure for 3G, but if you wish to do so, you can completely bypass it for LTE. And now you have complete control over which VAS and optimization services you need to scale based on how you define your steering policies. Next example is user Paul. So user Paul has opted in for a parental control service. So if he's on the 3G network, he will have to be steered to both the video optimizer as well as the parental control system. So this is a typical example of what we call in the industry service chaining. So his traffic needs to be piped to two different VAS optimization platforms. And the intelligent traffic steering device will make sure that takes place. And of course, in the reverse direction, you have to follow the exact same sequence of the traffic flows. Now, traffic steering and service chaining is obviously a topic that's also discussed a lot in the SDN environment. So people talking about SDN, software-defined networking, and it's a perfect use case to try to solve in an SDN type of environment. But what sometimes people overlook is that SDN is very much focused today still on layer 2, layer 3 type of forwarding, whereas in this type of environment, there's other functions that are required. And I hope this example illustrates a bit what I want to say here. Is let's take the example of user Paul again, which need to be traffic steered to both the video optimizer and the parental control system. So in the steering device, what happens is, first you assign that flow to a service chain based on your steering policy, and in this case we decided that it needs to go through both the video optimization as well as through the parental control systems. So the first action is the steering to the video optimizer. Now, that is actually two actions in one single shot. Action number one is steering to a pool, and action number two is load balancing across a series of video servers. And sometimes this is overlooked, and at the end, these problems are not so easy to solve. So you would still need some sort of a load balancing action to get traffic load balanced over video optimizers. Because if one of these video optimizer instances goes down, you obviously need to avoid steering traffic to it, and that is exactly what the load balancing function does. If, for some reason, all these video optimizer instances are down, you need to have some smart logic that bypasses that. So that's the other thing. The load balancer will then check if all these things are down. It will tell the steering flow that we need to either block all the traffic or bypass that particular VAS function. The second thing you see in the slide is that traffic steering is not always just piping all the traffic through. If you talk about a parental control service, in this case it's an ICAP call. So you're not steering all the HTTP content to that parental control system. You're actually doing an ICAP call, which is only part of the information sent to the VAS service. So that goes way beyond what you would find in traditional SDN type of networking. So I think it's clear that SDN is going to play an important role in this whole traffic steering service chaining concept. But things like health checking, things like load balancing will remain very important to make these architectures work and scale accordingly. So SDN, and that obviously also brings me to IETF, right? In IETF, I think about a year ago, maybe a little bit longer, they defined a service chaining working group. So the topic became so hot in the industry that IETF decided, let's create a working group and let's work out a few standards to define how this should work and how you should make this scale. And I'm not going to read what's on the slide here, but if you look at the charter of that working group, it really recognizes that IP networks rely more and more on advanced functions, which go way beyond layer 2 and layer 3 networking. So proxies, optimizers, firewalls, DPI platforms, right? And the goal of the service chaining working group is to find a model to dynamically pipe traffic through each of these individual functions. And if you look at what the charter is, it needs to be subscriber aware, it needs to be based on flow characteristics, etc. So it's actually everything I just described, really. So the IETF service chaining working group is essentially tackling the problems that I just described on how that is done today with an intelligent traffic steering device. So, and when you look at IETF, there's basically two main functional entities in this whole architecture. The first functional entity is what they call the service function chaining ingress function. So somewhere in that architecture, you need some entity that takes an intelligent decision based on policies for every packet that comes in that's going to determine where does this packet need to go to, which service functions does that traffic need to be piped through. So that is that SFC ingress function. The second part of what this working group is trying to solve is how do you do the actual forwarding? Once you have identified what is the service chain, as they call it, that flow needs to go through, how do you interconnect these different elements together, making sure that traffic both in the ingress and the egress direction goes through all these identified elements? So, and as you see in the example on this slide, if, for instance, this SFC ingress function defines that this flow needs to go through what is called service function chain ID number 1, it needs to go through the load balancer, then to the web proxy, then through the firewall, and then through the NAT44 device. So that's like need to pipe it through 4 service functions, if you will. SFC ID 2 is another one. So these two functions are really critical, and this is what's being discussed in the IETF. If I map that to what I already explained, and if I map that to what IETF is trying to do, then on the left-hand side is a representation of what I just explained, how the intelligent traffic steering device does all that work. So the intelligent steering device has all that contextual info, right, from radius, from the PCRF, from a DPI engine. It has all that knowledge. It has all that knowledge to take that intelligent decision on what VAS service that individual flow should go through. The second thing that steering device does is it actually controls the forwarding to all these elements. And it does that by means of a proxy functionality. So as you've seen on the previous slide, the steering device sends it to VAS1, and it load balances it as well. Traffic comes back, and then we know, now it needs to go to VAS3, traffic comes back, now it needs to go to VAS5, and traffic comes back. So that's how it works today. Works, very scalable, very flexible as well. It has this integrated load balancing, it has health checks, it has ICAP-based capabilities. Now what the industry wants to move towards is the model on the right-hand side. So this is the ingress classification function is separate from the traffic forwarding function. So you want to move away from the proxy type of steering into an SDN-based type of traffic forwarding between the different VAS elements. And if you look into the IETF draft, there are things like the NSH, the next services header being defined, so that the ingress classification function adds a specific header to the packets, so that these different VAS elements know exactly, based on that header, what to do with the packets and how to forward them to the next VAS service. So the message that I'm bringing you here is that the thing on the left-hand side is fully adopted. There's customers doing that today. It completely works. But obviously, people want to have a migration path to the model on the right-hand side. And in F5, that's exactly what we're doing. We're going to help our customers move from the model on the left-hand side, which is deployed today, into that IETF-endorsed model using these new standards on the right-hand side. So as I said in the beginning, this is not going to be a forklift upgrade. This is going to be a natural evolution path going from the left-hand side to the right-hand side. Of course, in this context, we will always talk about NFV as well, right? People want to completely virtualize the Gi-LAN, moving into a virtual EPC, moving into complete virtualization of all the Gi-LAN components. And a typical evolution path that we see is that in step one, you first virtualize all the VAS optimization layers. And what you can do in this case is that steering platform initially can remain a physical box, highly scalable, lots of capacity, lots of connections that can go through, and you keep that intelligent steering function right there, but step by step you sort of migrate your VAS and optimization platforms from a physical environment to a full-blown virtual environment. And of course, the orchestration tool will also talk to the steering platform, so that when at some point in time you need more capacity for video optimization, you just instantiate a new virtual machine with video optimization technology loaded onto it, and then you make sure the steering platform is aware of that additional capacity that he can steer to. So the steering platform will know at each point in time where are all these virtual machines supporting video optimization, where are all these virtual machines supporting security services, and we will dynamically modify the steering and the load balancing to all these components, completely orchestrated by that orchestration tool that you have. And that is typically a first step that we see some service providers looking into as a way to get into this NFV world in a step-by-step fashion. And of course, step two is all about completely virtualizing that NFV infrastructure. So what we see there is that people looking at how do I virtualize now that steering function? How do I scale it out by having multiple instances of that working in parallel? And then the whole SDN discussion comes into this as well, right? How do I move from that traditional proxy-based steering into this SDN-based steering, where tomorrow that next service header comes into the picture? So that's sort of a stepwise approach to NFV. So in a nutshell, market is demanding advanced steering capabilities for VAS offload. Why? Because traffic is increasing enormously. Continuing to scale up all these VAS optimization platforms to deal with all the traffic in your network is just economically no longer viable. You need to get more control on how each of these individual elements are being used, and you want granular control on how to steer traffic to them. Is it based on subscriber ID because you want to apply differentiation? Is it based on RAT type because you want to not use certain things for LTE versus using them for 3G? Is it based on congestion levels? We see lots of different use cases there, and everybody has a good reason to go for some of these. Second element is, that evolution path towards IETF-based service chaining. I hope I make that clear that what is available today can evolve to that IETF model based on SDN type of forwarding. So very important, that is not going to be a forklift upgrade. Solution that supports a wide variety of use cases. I think I covered that as well. Subscriber-based, RAT type-based, congestion-based, location-based, device type-based even. All these things are possible, giving you lots of granularity in terms of how to control that traffic steering thing. And last but not least, the ability to migrate from pure physical to full-blown virtual. I think that is key as well. Everybody's looking into how can I move from that physical Gi-LAN deployment into a virtual Gi-LAN deployment. And again, just like the traffic steering part of it, NFV should not be a forklift upgrade. It should be a step-by-step approach. And I hope again that in the previous slide I've shown you some ways of doing that in a step-by-step fashion. And with that, I reached the end of my presentation. I thank you all for joining, and I'm going to pass back the word to Tim. Over to you, Tim. Thanks a lot.
So, thank you very much, Bart, for that presentation. I'm sure everyone found that as interesting as I did. Now, as I mentioned earlier on, we have some time for Q&A. To submit a question, just type it into the comments box on this page, and Bart's answer will appear as text in the comment stream. There is no audio element to the Q&A. So it just remains for me to thank Bart and F5 Networks for making today's Telecoms.com webinar possible, and to thank everyone who joined us for the presentation. I hope you found it useful, and please look out for upcoming webinars that will explore other key topics affecting the telecoms industry today. See you again next time. Bye-bye.